In this extension set of 6f-2, we're going to look at simplifying non-perfect square roots and cubed roots. This tends to be more of an Algebra 2, a little bit geometry topic, but I just want to give you an overview just so that you can start to see what it'll look like. The idea here is we're trying to find the perfect square factors of the radicand to start simplifying radicals. So we're not going to put anything in decimal form here. We're going to leave it in radical form. And one of the ways we're going to do that is by using the product property of radicals. So that means that if I have two things multiplied together under the radical, I can split them into each their own radical, multiply them together, and they're still equivalent. An example of this would be if you have the square root of 4x, I can split that into the square root of 4 times the square root of x. Two radicals next to each other means multiplication. And the square root of 4 will simplify to 2, which can now be put with the square root of x. This is square root of 4x in simplest radical form. So for some reminders of your perfect square factors over here, remember these are 1 through 12 squared. So for instance, in number 1, think about 24. Think about the factors of 24 that are perfect squares. That is 24 divisible by any of these numbers over here? Well, when we get to that, we think that square root of 24 is equivalent to the square root of 4 and the square root of 6, because 4 times 6 equals 24. The reason I chose 4 and 6 instead of, say, 3 and 8 or 2 and 12 is because 4 is a perfect square. So when I simplify this, the square root of 4 is 2 times the square root of 6. So in simplest radical form, the square root of 24 is 2 square root of 6. Basically, we're pulling out any perfect square factors from these radicals in order to get them in simplest form. Think about 48. When we look at 48, we're going to think, are there any numbers that are factors of 48 that are in this list? 16 and 3 are. If you multiply 16 times 3, you get 48. And 16 happens to be a perfect square. So I'm going to choose that one because when I simplify the square root of 16, I get 4 square root of 3. In number 3, look at 72. Think about the factors of 72. You want the largest factor of 72 from this list. Now you could say, well, I could use 8 and 9. Well, 8 and 9 will work. If we take 8 and 9, we're going to end up with the square root of 8 times the square root of 9. And we know that 9 is a perfect square, so we get 3, still square root of 8. Square root of 8 can be simplified even farther to square root of 2 and square root of 4. So we would simplify the square root of 4 down to 2. We have the square root of 2 over here times 3. I can simplify by multiplying these two together to give me 6 square root of 2. Now we're going to pick a different set of factors, and when we do, we're going to see that it shortens our process up a little bit. So say I picked 36 and 2. 36 and 2 will speed along my process here. Square root of 36 and square root of 2. I know the square root of 36 is 6 square root of 2. So this way, if you used 8 and 9, is still perfectly equivalent. Okay, if you didn't see 36 and 2, you could totally use 8 and 9 and start working your way down. Just notice over here that we had an extra step to do because 8 could still be simplified farther, but you'll still end up with the same answer at the end. So if you don't see the bigger factors at first, using the smaller factors will still get you to the same answer. It just might take you a couple more steps. In number 4, the square root of 63. Think about factors of 63. Think about numbers that multiply together to give 63 that are perfect squares. You should be looking for 9 and 7. Square root of 9, square root of 7. We picked 9 because 9 is a perfect square. The square root of 9 is 3. So 3 square root of 7 is the simplest radical form of square root of 63. Take a look at 90. You should see 9 and 10. The square root of 9 times the square root of 10. I picked that set of factors because 9 is a perfect square. So when I simplify down, I'll get the square root, or I'll get 3 times the square root of 10. Say I wanted to do this a different way. Say I didn't see 9 and 10 right away, but say maybe I saw 2 and 45. Okay, well, 2 and 45 don't have perfect squares, but I know that 45 does. 45 can be split into 9 and 5. Well, the square root of 9 is 3, and I can take these two and multiply them back together, and we'll get 3 square root of 10. Not every set, like 2 and 45, that have no perfect squares will lead you here. Sometimes you just have to start from scratch and pick another set of factors. But in this case, that was another way that you could have gotten there. In number 6, when you look at 28, you're looking for factors that are perfect squares. Square root of 4 and square root of 7. 4 times 7 gives me 28. And then you're looking at 2 square root of 7. When you've got the square root of 84w, when you look at 84, start to think, is it divisible by any of the perfect squares? This one comes out to be divisible by 4 and 21. So 4 and 21 are both factors, and our w is stuck over here under a radical as well. So the square root of 4 is 2, 21 is as far as it can go, and w is also stuck under that radical because it can't go any farther than that. 32x squared. 32 can be split into the square root of 16, square root of 2. And then I know that if I take my 3 divided by 2, I'm going to get an x square root of x, because I would be able to divide this to get 1 with a remainder of 1. So I got 1x that's out and 1x that's still in. So square root of 16 is 4. That x can come out in front, and then still stuck under the radical is 2x. In number 9, we have the square root of 40, m to the 4th, n to the 3rd. Well, 40 can split into 4 and 10. Our m's, we're going to get an m to the 2nd that's out. From 4 divided by 2, we get m squared. From 3 divided by 2, we get 1 outside and 1 inside. 4 goes down to 2. My m squared's in front, my n is with it, and under the radical we have 10n. In number 10, the square root of 75 will split into the square root of 25 and 3. My p and my 5 divided by 2 gives me 2, remainder 1. So I'll have a p squared with still 1p underneath the radical, and q squared divided, take the square root of q squared and you get just q. Square root of 25 is 5. My p squared comes in front, followed by my q. The thing still stuck under the radical is the square root of 3p. The process works the same for cubes. So in perfect cubes, we can look and see what underneath our cubed root is divisible by our perfect cubes. So when you've got the cubed root of 40, this one splits into 8 and 5. So the cubed root of 8 times the cubed root of 5. Cubed root of 8 is 2. Then still times the cubed root of 5. The cubed root of negative 16 will split into the cubed root of negative 8 and the cubed root of 2. Cubed root of negative 8 equals negative 2 times the cubed root of 2. In 13, when we have 54, you're looking at the cubed root of 27 and 2. And then my 6 divided by 3 gives me x squared. That's on the outside. So cubed root of 27 is 3. X squared comes next to it, times the cubed root of 2. And in 14, 875, that's a big one, but what you are looking for is the cubed root of 125. I'm going to put my negative with that one, and my cubed root of 7. Cubed root of 125 is negative 5 times the cubed root of 7.